Hello everyone, today I'm going to introduce our work on biased scene graph generation from bias training. The proposed method can be concluded into 3 steps, but before diving into the details, I will talk about our motivation and some prerequisites. This paper aims to tackle the existing long-tail distribution problem of scene graph generation. It is also commonly observed in most of the real-world data. The problem is, it's not just making the existing methods to be highly biased, it also causes the model to predict only trivial relationships, simply because of their higher frequency. For example, trivial predicts on or near, dominating the output scene graph. You can imagine a detector detecting everything as an object. A dog is an object, a cat is an object, and the bicycle is also an object, which makes this whole task meaningless. While the proposed unbiased scene graph can successfully infer much more fine-grained predicates. To get started, I will introduce the concept of causal graph first. To understand why we need a causal graph, we should point out a common misunderstanding in data science. The input data is not the more the better. The problematic inputs can cause a prediction taking the false shortcut. Here is an example. To predict the crime rate, if we take all the related inputs, the ice cream sales and the temperature, the model could take the shortcut from S to C, which doesn't make sense. Why is it happening? Because in the summer, the temperature will increase, which causes the ice cream sales and the crime rate increase as well. With the help of causal graph, we know how to design the correct model and how to cut or separate the biased shortcut. Then I want to introduce the proposed unbiased inference into just 3 steps. The first step is the roadmap. We reconstruct the causal graph of the network to understand how it predicts the scene graph from an image. This causal graph has been adopted by most of the recent approach in scene graph generation. Although all edges in this causal graph are valid, they are not equal, so the shortcut can still occur and hurt the unbiasedness. That's why we need the next step. We use counterfactual thinking to identify the source of the bias. I visualize all 3 input variables for relationship prediction. They are object features, object labels, and background environment features. The conventional inference considers the entire model as a whole and only gives a one-time likelihood. But if we consider the model as a causal graph, the prediction can be intervened to perform the counterfactual thinking. For example, in scene graph generation, we found that even if we set the object features as dummy vectors, the prediction is still almost the same as the origin, which means the bottom right counterfactual case creates a shortcut. This is a pure blind guessing that we definitely want to avoid. So here comes the solution. Our final step applies the total direct effect that removes the above-mentioned bad bias and gets the unbiased part of the logics, which corresponds to the visual part but still under the same context. Note that our training phase is still conventional biased training, so we only need to run the inference model twice. The result is quite amazing. Given the same trained neural motif model, after applying our unbiased inference, we almost perfectly remove the long-tail distribution appeared in the performance. The tail categories can perform as better as the head ones. The only thing hinders the performance is the difficulty of each categories, but not the distribution anymore. There are 3 advantages of the proposed unbiased inference. It's model agnostic, simple, and effective. We compare 3 base models, neural motifs, VTransE, VC-tree, and 2 fusion functions, sum and gate. The TDE significantly improves the original likelihood prediction in all cases. We also compare conventional debias method, reweight, resample, and focal loss. Note that although reweight seems better than TDE in scene graph detection, but if we look at zero-shot recall, reweight got zero recall in the same scene graph detection, which means the unbiasedness of reweight is not generalized to new cases. We also test the scene graph-based retrieval. The improvement in retrieval means the TDE-based scene graph contains more discriminative information, so it can be easily retrieved. Here are the qualitative examples. The yellow box means conventional inference, and the green box means TDE-based unbiased inference. The interesting part is, for the button image, the conventional inference is totally blind. It considers that the girl is holding the kite even she didn't touch it, while the TDE-based inference correctly predicts the looking at relationship. Thank you for your patience. If you are interested in our work, please scan the QR code of our project and the paper links.
Hi everyone, this is Kathy. I'm going to talk about entity skeletons for visual storytelling. This is joint work with Ruo Ping and my professor Alan Black. This is briefly going to be the outline of today's talk. We have always been enveloped by narratives, let it be cavemen telling stories, puppet shows, to more contemporary media like movies, news, Instagram stories, etc. The ability to perceive and express a set of related content is fundamentally a human attribute, and it is our responsibility to impart the skill to machines. With some of the recent advancements in generating text, we are moving now towards making them more natural and human-like. We address one of the properties that bridges the gap between human and machine generation in this talk. While there are other properties such as surface forms and structure, I am going to present about the content property in this talk. For instance, the description of the first set of images mainly talk about beach, kids, palm trees and resort, etc. But it would not make sense if I talked about library or church. Similarly, the second set of images talk about library, books, etc. This contributes to the relevance property of the text. So for content relevance, we'll be looking into entities and their references in visual stories. In order to achieve this, we introduce anchoring. Now, what is anchoring? It is something that provides reliable and principal support by holding it consistently. In this particular case, guidance is provided in a fine-grained level. Each sentence SK in the output narrative is guided by a corresponding anchor unit AK. Broadly, the two components in NLP are natural language generation and natural language understanding, and anchoring provides for a synergy between them with a focus on generation. Here, we focus on the task of generating stories from a sequence of images, also known as visual storytelling. In addition to generating the story, our specific task is to improve the content relevance by introducing relevant entities at relevant junctions. Formally, the dataset comprises of a set of stories. Each story constitutes a sequence of 5 images denoted by I, image captions X, and stories in sequences Y. So the input is sequence of images DII, and the output is a story in sequences, and the anchor units are our entities. We evaluate our methods on the visual storytelling dataset. There are about 25% of the images for which the DII are absent, and we use a pre-trained image captioning model to derive DII in order to make it complete. The first step is to extract the entity anchors, which are also known as entity skeletons. This is defined as a linear chain of entities and their corresponding referring expressions. We work with 3 forms of entity anchors. The first is the surface form coreference chain, the second are nominalized representation, and the third is abstract property representation. More details of these anchors are in the paper. First, let's look at the baseline, which is essentially a seek-to-seek model that extracts visual features followed by a bidirectional LSTM that extracts local and global features. We improved this model to make a fair comparison and a stronger baseline by augmenting the decoder with the entity skeleton words. In addition, we also proposed a multitask skeleton prediction model which generates the sentence as the primary task and the secondary task being the skeleton entity prediction. This is our main model, which is the hierarchical global model, which extracts sentence level features and story level features. So essentially, we perform hierarchical attention, one at word level for each sentence and then sentence level for the entire story, and use it while decoding each sentence. Here are some of the evaluation metrics that we concentrated on. As we can see, multitask generation model and the global attention model improved the automatic metric Meteor. Coming to the distance metric, we computed the Euclidean distance between the generated stories and the goal stories by extracting entities from each of them and comparing the distance between them. The last column shows the number of distinct entities in the generated stories, and this value for ground truth stories is 0.7944, and this number is closest to the hierarchical global attention model. We also conduct human evaluation, which resulted in a preference of 82% over the baseline and 64% over the multitasking model. Here is an example story. The highlighted words were generated in the right frame with respect to the ground truth story. The baseline model got the skeleton words right for sentences 4 and 5, and the global hierarchical attention model could do it for sentences 1, 3, 4, and 5. So the main takeaways are it improves relevance component of visual storytelling, improves controllability in generation, and it is a step towards interpretability with respect to intermediate representation. Thank you.
Hi, I'm Arka from USC and I will be presenting our CAPR 20 work on video object grounding using semantic roles in language description. This is work done with Kanchan and my advisor Professor Ram Nevashia. In video object grounding, given a sentence and a video, we want to localize all the referred objects. In this example, we want to ground the man, the ball, and the group of kids participating in the passing verb. However, for many object categories, only one instance is present in the video, and these objects can be localized using just an object detector like FastRCNN. For instance, here all can be localized independent of the context from the man or the kids. As a result, object relations are largely ignored for the task of video object grounding. Essentially, we would like to know if there was another ball in the video, would the model still ground the correct ball? To elevate the role of object relations, we propose two steps. First step is contrastive sampling, where for a queried description such as man petting a dog, we retrieve new videos from the dataset having the same semantic role structure, arg0, verb, arg1, but one role is realized by a different noun or a verb. In this example, we get three contrastive samples: woman petting a dog, man picking up a dog, and man petting cat. In the second step, we merge the videos temporally and spatially. The merged video now contains multiple instances from the same object category. Therefore, the model must now consider object relations to disambiguate and ground the correct instance. To encode object relations, we apply self-attention using a transformer network. We observe that different objects could have multiple relations even in the same video. To account for this, in addition to an object transformer, we propose a multimodal transformer that takes both object and phrase features as input. We further note that transformer networks require positional encodings. However, absolute positions are not meaningful in a video. Thus, we propose relative position encoding derived from a prior work in machine translation. Essentially, it biases the model to weigh related objects based on their proximity. This results in our framework VOGNet, which combines a grounding model with object and multimodal transformers with relative position embeddings. For evaluations, we contribute ActivityNet SRL, where we append semantic roles to ActivityNet captions and align the phrases with the bounding boxes from ActivityNet entities. The dataset is available on GitHub. For results, we consider a simplified case GT5 where we sample only 5 boxes per frame with a preference for the ground truth boxes. This achieves a recall score of 86% and allows for rapid prototyping and experimentation. First, we notice that models trained on single videos without augmentations fail miserably at the temporal and spatial cases where it gets a mere 3%. This validates our hypothesis that models trained on single videos ignore object relations. We partially address this by training with temporal and spatial augmentations of contrastive samples, reducing the gap by over 20%. Even so, there still exists a large gap to be filled. It is interesting to note that models trained with augmentations on even randomly sampled videos achieve similar performance to those trained with contrastive samples. However, random samples are not good for evaluations where a model can find the correct video 75% of the time. This implies contrastive sampling is imperative for evaluation. In our ability studies, we find adding relative position encoding gives almost 1% boost on strict accuracy over object transformers. Furthermore, adding even 2 more layers of object transformer falls short of a single layer of multimodal transformer. This validates the contribution of VOGNet over competitive baselines. To summarize our work, first, we study video object grounding and enforce learning object relations via spatial and temporal concatenations with contrastive examples. Second, we contribute ActivityNet SRL as a benchmark for video object grounding. Third, We propose VOGNet, which has multimodal transformer and relative position encoding. Finally, to foster reproducibility, we have open sourced our code on GitHub with pre-trained models, training logs, and dataset. Come talk to us for more details, and thank you for listening.
Hello everyone, I'm Yuan Kaiqi. I'm happy to present our work here. We humans have a long-haul goal, which is to build intelligent robots that can perceive environment, execute commands, and communicate with humans using natural language. Toward this goal, researchers have devoted considerable efforts on related tasks, such as visual question answering, referral expression grounding, and language-guided navigation. However, they cannot reflect many of the most appealing uses of robots, which requires communication about a remote object. For example, bring me the blue cushion from the living room. So here we propose a new task and dataset, named Reverie, to make a step forward. Let's see a demo of this task. The agent is given a natural language instruction referring to a remote object. The agent must navigate to an appropriate location and identify the target. The agent can look up, look down, and look around at each step. The blue cylinders indicate nearby navigable viewpoints provided by the simulator. Then, what's the challenge of this task? First, the appearance changes greatly even for the same object, in terms of shape, scale, or aspect ratio, caused by different camera views. Second, the instructions involve various linguistic phenomena, such as dangling modifiers, spatial relations, and imperatives. Third, it's difficult to understand the instructions. On one hand, the instructions are very short. On average, it's 11 words less than those of the room-to-room navigation dataset. On the other hand, about 56% of instructions mention 3 or more objects, falling into nearly 500 categories. As the Reverie task involves both room-to-room navigation and referring expression grounding, an intuitive solution is to combine state-of-the-art navigation and grounding models. There are two ways to combine them together. The first one is to perform grounding when a navigation ends. The other one is to perform grounding at each navigation step. Here we implement the second combination manner using an interactive navigator pointer model. At each step, the pointer outputs labels and visual features of top 3 objects matched to the instruction, which are further encoded and concatenated by the interaction module. Finally, the navigator predicts the next navigation action based on the concatenated visual feature and the instruction. Now let's have a look at metrics. A task is considered successful if it selects the correct object from a list of candidates, or the predicted bounding box has an IOU no smaller than 0.5 with ground truth. Then the performance of a model is mainly measured by the remote grounding success rate. We also measure navigation performance with 4 kinds of metrics. Please note, in our task, a navigation is considered a success if it stops at a location within 3 meters to the target object. Here are the results using MATNET as a pointer. It shows that performing visual grounding at each navigation step achieves the best performance, with an RGS of 11%. However, this is still far behind human performance. This indicates significant necessity of researches in this field. We get code and dataset available online. Thanks for your attention.
Hi, I'm Shizhe. I'm going to introduce our work for fine-grained video text retrieval. Video text cross-model retrieval is using sentence to retrieve desired video content. The dominant approach is to learn a joint embedding space. However, in global match methods, it's usually hard to encode fine-grained details, while in local match methods, relationships between local vectors are not well captured. So in this work, we propose a hierarchical graph reasoning model. We decompose video text matching into 3 hierarchical levels for events, actions, and entities to capture global to local information. For the textual encoding, we decompose sentences into semantic row graph and capture relationships via graph reasoning. For the video encoding, we use different levels of text to guide the learning of diverse video representations. Our model achieves better performances in in-domain cross-domain retrieval and fine-grained binary selection. Our codes and datasets will be released in the following link. Thanks for your attention.
Hello everyone, I'm Ning Weipan from JJR Research. It's my great pleasure to present our new work for image captioning that employs higher and even infinite order inter-model and inter-model interactions while designing a linear attention block. So compared to the conventional attention mechanisms in image captioning, which inherently employs only the first order feature interactions, our design as linear attention block can fully employ bilinear pooling to measure both the spatial and channel-wise bilinear attention distribution to capture the second-order interactions among the inputs. Higher and even infinite order feature interactions can be modeled through stacking or equipping the block with the ELU. Furthermore, we also present the X-linear attention network that integrates X-linear blocks into an image encoder and a language decoder. Experiments are conducted on COCO, which obtain to date the best performance. So, besides, we currently release a new video language pre-training dataset we can to use.
This is Hong Yuzhen from UC Merced. I'm glad to share our work, RetrieveGAN, image synthesis via differentiable patch retrieval. It is a joint work with Xinyin Li, Lu Jiang, Weilong Yang, and Mingshen Yang. In this work, we aim to generate image from the scene graph representation. The input signal is a scene graph, which indicates the object in the scene and the relationship between objects. Here is a demonstration of our method. Given the input scene graph, our model learns to retrieve patch for each object from the real images. Our model then synthesizes the final image according to the retrieved patches. There are 2 challenges in our approach. First, the retrieval process is usually not differentiable since we need to sample from a discrete distribution using the argmax operation. As a result, the retrieval process cannot be optimized during the GAN training stage to consider the realism of the synthesized images. Second, the selected patches need to be mutually compatible. For instance, an existing retrieval-based approach may select soccer player along with the baseball court, which should not appear in the same image. Here is an overview of the proposed RetrieveGAN model. Our contributions are in the retrieval process. First, we use the Gumbel softmax trick to make the retrieval process differentiable. Second, we design an iterative retrieval process to select mutually compatible patches. The Gumbel softmax trick involves 2 operations. Gumbel reparameterization enables us to model the discrete distribution using the continuous distribution. The softmax operation approximates the argmax operation in the retrieval process. Since all the operations here are differentiable, we can optimize the patch embedding function during the GAN training stage. Now, given the differentiable mechanism, how can we select mutually compatible patches? We design an iterative retrieval process to select mutually compatible patches. In each iteration, the core idea is to retrieve the patch which is most compatible to the patches that are selected by the previous iterations. We iterate this process until all the objects in the input scene graph are assigned with an image patch. After the retrieval process, we encourage the selected patches to be mutually compatible using a co-occurrence loss function. Specifically, we minimize the feature distance between the selected patches on the co-occurrence space. The co-occurrence mapping function is a pre-trained function using a triplet loss on the training images. The positive pair contains the patches from the same image, while the negative one contains the patches from different images. We conduct experiments on 2 standard benchmark datasets and compare to several state-of-the-art approaches. Since the retrieval process can be optimized by the GAN training, our method reports more favorable realism scores. Here we show an example qualitative results. Compared to the previous retrieval-based framework, our method can select more compatible patches which yield more appealing results. To conclude, for the scene graph to image synthesis problem, we propose a retrieval approach that can be optimized during the GAN training stage and selects mutually compatible patches for generating the final image. Thank you.